Okay, the last big topic for Calc 1 is antiderivatives. Okay, so now we're going to do something a little different. But first, let's do a really quick review of the course. Okay, we start with limits, and then we use limits to define the derivative, right? That limit definition, and then we had shortcuts. And now we're going to do limits to do what's called an integral. It's going to look like this. And what this means is actually find the antiderivative, the function where this is the derivative. So in other words, I'm going to give you the derivative, and you're going to find a function that has that derivative. Okay, and then I'll make the connection at some point. It's not as straightforward, but I'll show how limits give us this, what's called an integral. Okay, so, and that's all Calc 1 really. This is our last topic, is finding antiderivatives, and we'll do a pretty deep dive into them. Okay, so let's start with our first example. See if you can figure this out. Here's a derivative. Find a function that has that derivative. So you might say, okay, this is f prime. I say f is, it's got to have an x cubed in it, right? Because if I were to take, the check's always going to be to take the derivative of my answer and see if I get that. And it turns out I gave you an easy one. If you take the derivative of my first guess here, you bring the 3 down, then you take 1 away, and then you're right. So this is the antiderivative, right? If this is the derivative, this is the antiderivative. All right, any function you get as an antiderivative, once you take the derivative, it should work, right? The derivative of your answer. Now, can you think of another one? I can think of a bunch of functions. Say, well, okay, if I take the derivative of f, I get f prime. But if I take the derivative of this function, we'll call that f1. I can think of another one. What about this? What's the derivative of that? Well, you get 3x squared, and then that would go away. All right, I can think of another function. Right? All of these derivatives, they all have the same, they all change the same. They might start somewhere else, but they all change the same. They all have the same derivative. In other words, this constant, of course, doesn't matter, because when you take the derivative of constant, you get 0. So we're going to have a way to write that, or actually the directions are going to be different. So let's look at my next example. I guess I said the same question. It's almost the same question. My first question was find a function. So these would all be okay. But now the next question, which is very similar, this is how your homework will word it, and we'll do some homework problems in a second. Find all the antiderivatives. Well, that means that all the antiderivatives of that are, and then we're going to use a really important letter here that we'll see all the time, plus c. Okay, that represents a constant. You're going to see this all the time. Okay, and now for our new notation, this integrand symbol, you're going to be writing this all the time, so get used to it. This is, we've seen this before when we took derivative dx. It's differential. We can think of it right now as antidifferentiate with respect to x. That is, when you get to Calc 3, there'll be other variables in here. But right now, we just have to understand that this will always match with that. Okay, and this means my answer should be a function of x. So it'd be x cubed plus c. So now we don't have the wording would be find all antiderivatives of this function. That's what this means. Okay, this integral symbol means find the antiderivatives of this function, and not just find one, but find all. So we have to do the plus c, right? Because any constant I took the derivative would be 0. And if we wanted to do the check, which we can do, I know this is a basic function, but the check goes like this. You take the derivative of your answer with the plus c, and you got to get this or this, right? And it'll work out because you get 3x squared plus 0. All right? So that's the basic concept for what we're going to be doing going forward. And let's do a couple examples. Find all antiderivatives. Remember, that would be the same as, this is equivalent to this question. Okay, so what's the antiderivative of cosine? Well, the 6 will come along for the ride. I'm going to write sine, because I know if I take the derivative of sine, I get cosine. And derivative of what function just gives you 3? That should be 3x. And then I do a plus c. Right? These are a little trickier, so you can always do the check. I'll stop doing the check for the sake of the video length, but the check goes like this. You just take the derivative of this thing and you see what you get, right? And the derivative sign is cosine, constant multiple rule, derivative of 3x is 3, derivative constant is 0, and I'm right. All right, so now remember in calculus we like to do algebra first. This means take the antiderivative and do the plus c thing, but that looks like a mess. So first I want to rewrite it using my algebra knowledge. That's x to the 1/2 and it's in the denominator, so that's a negative 1/2. That's x to the 1/2 and it's not in the denominator, so that's x to the 1/2. And then I anti-differentiate using the power rule backwards, okay? So let's see if we can go ahead and figure out this power rule that goes backwards. Instead of subtracting 1, you got to add 1, right? And then what did we do? How did we figure that out? Let's look at this again. It was 3x squared. When I took the antiderivative, the 3 was gone, right? So I was like, so if this 3 comes along for the ride, and then when I add 1 to this, what do I have to do? I have to divide by it in order for it to go away. In other words, you're dividing by your new power, right? And then that's what gave me the x cubed plus c. We just kind of figured it out. But if I want to rule, then that means I'm going to have to divide by my new power and do the plus c thing, right? So, for example, let's just do an easier one. I can't change my color, why not? Something's going on with my pen here. What if I just said, let's do an extra example. What if I just said, find this? Well, you know you have to add 1. That's the easy part. Well, try that again. Adding 1, not subtracting 1. Right? So I added 1 because I'm going the other way. I'm finding the antiderivative. I do the plus c thing. But this isn't right because if I took the derivative of that, I'd have a negative 7 out here. I'd bring the 7 down, I'd have a negative 7. I'd take 1 away and I'd have that negative 8. That would be good. But that negative 7 will be hanging out, so I have to divide by it. Right? And now if I did the check, negative 7 comes down, they cancel out, take 1 away, negative 8 plus c, and I'd be right. Okay, so this is my power rule for anti-differentiation. So let's use it. So the 7 comes along for the ride. I'm going to add 1 to negative 1/2. So negative 1/2 plus 1 is positive 1/2. And I'm going to divide by my new power. How about this one? 7 comes along for the ride. Add 1 to 1/2. That's 3 halves. I'm going to divide, and you might realize that this is a little messy. Dividing by 3 halves is the same as multiplying by 2/3, right? And that's how we're going to deal with this one. Let's see if I can get some more space here. So instead of dividing by a fraction, we know it's better to multiply by the reciprocal. Dividing by half is the same as multiplying by 2. Dividing by 3 halves is multiplying by 2/3. And there's my answer. Again, I'll skip the check now just for the sake of video length, but check that. If you take the derivative of that, you should get this. Okay, back on that idea of doing some algebra before the calculus. I don't have like a product rule yet, right? This is a product of two functions. Maybe there'll be a product rule in the future, maybe not. Integration is typically a little more complicated than differentiation. So, but we're not worried about that now. We just need to figure this out. So what would you do? You get the product of two functions. We want to eliminate the product by go ahead and multiplying. So we got to do some algebra first, or some arithmetic. I guess it's algebra. 36m cubed minus 40m squared dm. And now I can take the derivative. 36 comes along for the ride. Just m cubed, what is that? You go m, add 1, divide by the new power. 40 comes along for the ride, add 1, divide by the new power. Plus c, and now clean it up. 36 over 4 is 9. 40 over 3 is just 40 over 3. And I'm done. Differentiate to check. See if it's right. Oh, good, a trig problem. So trig, what you can do, you say, what function has the derivative that's secant squared? That's easy. That's the tangent function. The antiderivative of 9x, or of 9 is 9x plus c, done. Okay? All right, and now we do this. So now the question is, what if I wanted to know what c was? Okay, that is if I want one particular, remember this is all of the antiderivatives. There's an infinite amount because I can tack on any constant and I have an answer. Well, there's something called initial value problems where they're going to give you a little more information so that you can find c. Okay, so they want one function now and they'll give you this information. Okay, so let's take a look. So for the function below, find the antiderivative of f that satisfies this initial condition. That is something about the antiderivative that they're using capital F for. Okay, so just a thing about notation. So far I've been doing this. So here's f prime, find for me f. Sometimes they'll just say, here's a function, find for me the antiderivative, and they'll use a capital F. Okay, don't let that confuse you. It's all the same thing. Pretty much every problem now is going to be, here's a derivative, even though it's not labeled as a derivative, and they want you to find the antiderivative. Okay, whether they call it a derivative or not, the process is the same. Okay, so we're going to do the same that we did before. We're going to find the antiderivative of this thing. And I'm going to add 1, divide by the new power. 3 comes along for the ride, add 1, divide by the new power. If it's a constant, you just put an x on there. Okay, so that's what we did before. That's the general antiderivative, or all antiderivatives. I'm going to clean it up a little bit here. Negative 1 over negative 3 is plus 3. X to negative 1, I'll write it like that. Usually we don't want to write negative exponents in our answer. And this is f. This is what they're calling big F, all right? Now they're telling us big F of 1 is equal to 0. So I just plug that in. Big F of 1, so that means x is 1, 1/7 plus 3 over 1 minus 5 times 1 plus c. And big F of 1 equals 0. So I plug in 1 for x and 0 for the output, and that will always allow me to solve for c. Okay, and then what we're doing is finding one particular antiderivative. So let's see, 1/7 plus 3 minus 5 plus c equals 0, which means c equals, well, I can combine those. That would be negative 2. Well, I guess we could just add them all together. Let's do that. What's 1/7? 3 minus 2. 2 would be 14 over 7. So 1/7 minus 2 is 1/7 minus 14/7. So that's negative 13/7. Quick algebra problem. And now I can write my answer. F of x for this particular value, f of 1 equals 0, is equal to this thing. Well, yeah, let's just rewrite it. X to the 7th over 7 plus 3 over x minus 5x plus c. We always wrote c before, but now I'm able to find c because they gave us that initial condition. Okay, so that would be c value of negative 13 over 7. And that is my answer. And if you wanted to check your work, you take the derivative and you should get the original function. And also you could make sure f of 1 equals 0 by plugging in 1. 1/7 plus 3 minus 5 minus 13/7. That should be equal to 0. Should be 0. Okay? All right. Couple more problems. Do them I'll do these in the next video.